The universe as we know it, vast, infinite, and teeming with galaxies, began as something unimaginably small, smaller than an atom, a single point of infinite density and heat, a cosmic seed that sprouted into everything we see today. This is the story of the Big Bang, but it's only the beginning of a much larger mystery. What sparked the birth of everything we know? Are we alone in this universe, or could there be countless others, each with its own laws of physics and reality? Today, we're taking a journey through the most riveting theories about the genesis of the universe, from the explosive moment of creation to the tantalizing possibility of a multiverse. Together, we'll explore how scientists piece together the origins of existence and why these questions matter not just to physicists but to all of us. So, let's dive into the mysteries of creation and uncover the stories that shape our understanding of the cosmos. Picture this, a single, unimaginably dense point, smaller than the head of a pin, containing all the energy and matter that would one day become stars, planets, and galaxies. 13.8 billion years ago, this tiny speck exploded in a cataclysmic event we now call the Big Bang. It wasn't an explosion in the traditional sense, like fireworks or a supernova, but rather the rapid expansion of space itself, a stretching of the fabric of reality that set the stage for everything we see today. This moment marked the birth of time, space, and the universe as we know it. But how do we know this actually happened? The story of the Big Bang theory begins not with a single discovery, but with a series of clues that scientists pieced together over decades. One of the most compelling pieces of evidence is the cosmic microwave background radiation, a faint glow that permeates the entire universe. Think of it as the afterglow of that initial explosion, a cosmic fingerprint left over from the universe's fiery infancy. This radiation was first detected accidentally in the 1960s, and it matches perfectly with what the Big Bang theory predicts. It's like finding a photograph of the universe when it was just a baby, giving us a glimpse into its earliest moments. At the heart of the Big Bang lies a concept called the singularity, a point of infinite density and temperature where the laws of physics as we know them break down. Imagine squishing the entire universe into a space so small it defies comprehension. From this singularity, the universe began to expand and cool, setting off a chain reaction that led to the formation of atoms, stars, and eventually galaxies. Pioneers like Georges Lemaitre, a Belgian priest and physicist, first proposed the idea of an expanding universe in the 1920s. Decades later, Stephen Hawking and others refined the theory, helping us understand how this initial spark gave rise to the cosmos we inhabit today. The timeline of the Big Bang is a story of transformation. In the first fraction of a second during what's called the Planck epoch, the universe was a seething, chaotic mess of energy. As it expanded, it cooled, allowing particles to form and combine. Within minutes, the first protons and neutrons came together, creating the building blocks of matter. Over millions of years, gravity pulled these particles into clumps, forming stars and galaxies. To put it in perspective, imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move farther apart, just like galaxies drifting away from each other in an ever-growing universe. Yet, for all we know, the Big Bang raises as many questions as it answers. What existed before that moment? Was there a before at all? These questions push the boundaries of our understanding, challenging us to think beyond the limits of space and time. The Big Bang isn't just a scientific theory, it's a gateway to exploring the deepest mysteries of existence, inviting us to wonder about the very nature of reality itself. The Big Bang gave us the universe, but it didn't explain everything. Why is the cosmos so uniform on a large scale, with galaxies spread out in a way that seems almost too perfect? Enter cosmic inflation, a theory that takes the story of the universe's birth and adds a dramatic twist. Proposed by physicist Alan Guth in the 1980s, inflation suggests that the universe didn't just expand after the Big Bang, it did so at an astonishing, exponential rate. For a fraction of a second, space itself stretched faster than the speed of light, smoothing out irregularities and setting the stage for the universe we see today. It's like blowing up a balloon so quickly that every wrinkle disappears, leaving behind a smooth, even surface. This rapid expansion wasn't just a random event. According to Guth, it was triggered by a quantum fluctuation, a tiny, random ripple in the fabric of reality. Think of it as a cosmic spark that ignited the fire of creation. This fluctuation caused space to stretch exponentially, transforming a microscopic region into a vast, uniform universe. It's a mind-bending idea, but one that solves some of the biggest puzzles in cosmology. As Guth himself put it, the universe is the ultimate free lunch. Inflation explains why the universe looks the same in all directions and why its temperature is so consistent, even in regions that should have never been in contact with each other. But how do we know this actually happened? The evidence for inflation lies in the way galaxies are distributed across the cosmos. Observations show that the large-scale structure of the universe matches what inflation predicts. Clusters of galaxies spread out in a pattern that reflects that early, rapid expansion. Another clue comes from tiny ripples in the cosmic microwave background, the afterglow of the Big Bang. These ripples, imprinted during inflation, are like fingerprints left behind by the universe's earliest moments. They tell us that something extraordinary happened in those first fractions of a second, something that shaped the destiny of everything we see today. Inflation doesn't just fill in the gaps of the Big Bang theory. It opens up new questions about the nature of space, time, and the fundamental forces of the universe. What caused that quantum fluctuation? What powered the rapid expansion? And could there be other universes out there, each with its own version of inflation? These mysteries lead us to the next chapter in the story of the cosmos, the role of dark energy, the mysterious force driving the universe's expansion today. But that's a tale for another moment. For now, cosmic inflation reminds us that the universe is full of surprises, each one more fascinating than the last. What if everything we know, our universe, our laws of physics, even our own existence, is just one thread in an infinite cosmic tapestry? This is the heart of the Multiverse Hypothesis, a mind-bending idea that suggests our universe might be just one of countless others, each with its own unique set of rules. Picture a vast ocean of universes, each one a bubble floating in an endless sea of possibilities. Some bubbles might be eerily similar to ours, with planets, stars, and even life forms that resemble what we know. Others could be utterly alien, governed by laws of physics so strange they defy imagination. This isn't science fiction, it's a serious scientific theory that emerges from some of the most cutting-edge ideas in physics. The multiverse hypothesis isn't just a single idea, it's a collection of theories that point toward the same astonishing possibility. One of the most compelling comes from the concept of eternal inflation, an extension of the cosmic inflation we discussed earlier. According to this idea, inflation didn't just happen once, it's still happening, constantly spawning new universes like bubbles in an ever-expanding cosmic foam. Each bubble universe could have its own unique properties, from the strength of gravity to the number of dimensions. Physicist Brian Greene describes this as a cosmic kaleidoscope, where every twist and turn reveals a new, unpredictable reality. Another avenue to the multiverse comes from string theory, a framework that tries to unify all the forces of nature. String theory suggests that there could be as many as 10 to the 500 possible configurations for the universe, each corresponding to a different set of physical laws. Max Tegmark, a cosmologist and multiverse advocate, categorizes these possibilities into 4 levels, ranging from universes with slightly different initial conditions to entirely separate realms with completely different laws of physics. It's a staggering idea, one that challenges our understanding of reality itself. But how do we make sense of something as abstract as the multiverse? Think of it like a library where every book tells a different story. In one book, gravity might be stronger, making stars burn out faster. In another, the fundamental constants of nature could be tweaked, leading to a universe where life as we know it is impossible. Or perhaps there's a universe where everything is identical to ours except one tiny detail, like the color of the sky or the outcome of a key moment in history. Could there be another version of you in a parallel universe, living a life that's almost the same but not quite? The multiverse has captured the imagination of not just scientists but also storytellers. From the Marvel Cinematic Universe to science fiction classics, the idea of parallel realities has become a powerful metaphor for exploring questions of identity, choice, and destiny. Yet, while pop culture often simplifies the concept, the scientific version of the multiverse is far more nuanced and far more mysterious. Of course, the multiverse hypothesis isn't without its critics. Some argue that it's untestable, as we can't observe or interact with other universes. Others worry that it pushes the boundaries of science into the realm of philosophy. But for many physicists, the multiverse isn't just a wild idea. It's a natural extension of our current understanding of the cosmos. It challenges us to think bigger, to ask questions we might never have considered before. What does the multiverse mean for us? If there are infinite realities, does it diminish the uniqueness of our own? Or does it make our existence even more extraordinary, a rare and precious thread in an infinite cosmic fabric? These questions don't just belong to physicists, they belong to all of us. They invite us to wonder, to dream, and to explore the infinite possibilities that lie beyond the edges of our universe. Imagine the universe as a grand symphony where every particle, every force, and every ripple of energy is a note in an intricate cosmic melody. At the heart of this symphony lies a profound idea that the building blocks of reality aren't particles or waves, but tiny, vibrating strings. This is the essence of string theory, a revolutionary framework that seeks to harmonize the discord between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. String theory proposes that everything in the universe, from the tiniest quark to the largest galaxy, is made up of these one-dimensional strings. Each string vibrates at a unique frequency, much like the strings of a violin, creating the distinct notes that correspond to different particles and forces. An electron, for example, might be a string vibrating at one frequency, while a photon, the particle of light, could be another. It's a beautiful, unifying idea, one that suggests the universe is far more interconnected than we ever imagined. But here's where it gets even more fascinating. String theory doesn't just stop at the familiar 3 dimensions of space and 1 of time. Instead, it requires up to 11 dimensions to make the math work. Picture this: our universe might be like a sheet of paper with the 3 dimensions we experience: length, width, and height, visible on its surface. But what if that paper had hidden folds, representing extra dimensions curled up so tightly that they're invisible to us? These extra dimensions could be the key to unlocking the deepest mysteries of the cosmos, from the nature of gravity to the existence of dark matter. Edward Witten, one of the most influential figures in string theory, once described it as a piece of 21st century physics that fell into the 20th century. It's a theory that pushes the boundaries of our understanding, offering a glimpse into a reality far stranger and more elegant than anything we've encountered before. Michio Kaku, another prominent string theorist, likens the extra dimensions to the harmonics of a musical instrument, subtle, hidden layers that give the universe its richness and complexity. Now, let's take a moment to imagine what life might be like in a higher dimensional universe. In our three-dimensional world, we can move forward and backward, left and right, up and down. But what if there were a fourth spatial dimension? Objects could move in ways we can't even visualize, appearing and disappearing as they shift through unseen directions. It's a mind-bending concept, one that challenges our most basic assumptions about reality. String theory isn't just a scientific pursuit. It's a journey into the unknown, a quest to uncover the fundamental fabric of existence. While it's still a work in progress with many questions yet to be answered, it represents one of the most ambitious attempts to understand the universe at its deepest level. And as we explore its implications, we're reminded just how vast, mysterious, and awe-inspiring the cosmos truly is. So, what does string theory mean for us? It's a reminder that the universe is far more complex and interconnected than we often realize, with layers of reality waiting to be discovered. Whether or not string theory proves to be the ultimate description of the cosmos, it invites us to think bigger, to dream of possibilities beyond the limits of our current understanding. And in that sense, it's not just a theory, it's a symphony of ideas playing the music of the universe itself. What if the universe isn't a one-time event, but an eternal dance of creation and destruction, endlessly repeating itself? This is the essence of the cyclic model, a theory that flips our understanding of the cosmos on its head. Instead of a single Big Bang marking the beginning of everything, this model suggests that the universe goes through an infinite series of expansions and contractions, like the breathing of a cosmic giant. Each cycle begins with a Big Bang, expands into a vast, intricate universe, and eventually collapses back into a dense state, only to explode again in a never-ending loop. At the heart of the cyclic model is a radical idea. The Big Bang wasn't the beginning, but just one moment in an infinite sequence. This theory elegantly sidesteps the singularity problem, that mysterious point of infinite density where the laws of physics break down. Instead of a single, inexplicable origin, the cyclic model proposes that the universe has always existed in some form, cycling through phases of growth and renewal. It's like imagining time as a circle rather than a straight line, with no true starting point or end point. One of the most intriguing aspects of this model is the role of branes, short for membranes. According to physicists Paul Steinhardt and Neil Turok, our universe exists on a three-dimensional brane floating in a higher dimensional space. Picture two sheets of paper, each representing a brane moving parallel to each other in an unseen dimension. Every few trillion years, these branes collide, releasing an enormous amount of energy that triggers a new Big Bang. It's as if the universe is a cosmic accordion, expanding and contracting with each collision, creating new cycles of existence. But how does this reconcile with what we know about the Big Bang? The cyclic model doesn't dismiss the Big Bang. It reimagines it as part of a larger, more dynamic process. The afterglow of the Big Bang, the cosmic microwave background, and the distribution of galaxies all fit within this framework. The key difference is that the cyclic model avoids the need for a singularity, offering a more elegant explanation for the universe's origins. It also provides a natural solution to some of the Big Bang's lingering mysteries, like why the universe is so uniform on a large scale. Imagine standing on the shore of an endless ocean, watching waves crash against the sand. Each wave rises, peaks, and falls, only to be replaced by another. Now picture the universe as that ocean, with each cycle of expansion and contraction like a wave on its surface. Could it be that the universe has no true beginning or end, but simply exists in an eternal rhythm? This idea challenges us to rethink not just the nature of the cosmos, but our place within it. The cyclic model also opens up fascinating possibilities for the future. If the universe is truly cyclic, then everything we see, the stars, galaxies, and even life itself, might one day be reborn in a new cycle. It's a humbling thought, one that invites us to consider the impermanence of everything we know, while also hinting at the possibility of renewal on a cosmic scale. Of course, like any groundbreaking theory, the cyclic model has its skeptics. Some argue that it's difficult to test, as the evidence for previous cycles might be lost in the collapse and rebirth of the universe. Others question whether the model can fully explain the fine-tuning of the universe's physical constants. Yet, even with these challenges, the cyclic model offers a compelling alternative to the traditional Big Bang narrative, pushing us to explore new frontiers in our understanding of existence. So, what does it mean for us to live in a cyclic universe? It's a reminder that the cosmos is far more dynamic and mysterious than we often realize. Whether the universe had a single beginning or is part of an eternal cycle, the questions it raises are as profound as they are unanswerable. They invite us to marvel at the beauty of the cosmos, to wonder about its endless possibilities, and to keep seeking answers in the vast, ever-changing tapestry of reality. What if everything you see, touch, and experience, every star, every galaxy, even your own body, is nothing more than a projection, like a movie playing on a cosmic screen? This is the startling idea at the heart of the holographic principle, a theory that suggests our three-dimensional universe might be a hologram encoded on a two-dimensional surface. It's a concept so radical that it challenges our most basic understanding of reality. The holographic principle emerged from the study of black holes, those mysterious regions of space where gravity is so strong that nothing, not even light, can escape. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder, and that this entropy is proportional to the surface area of the black hole's event horizon, not its volume. This was a surprising result, hinting that all the information about what falls into a black hole could be stored on its two-dimensional boundary. Building on this insight, physicists Leonard Susskind and Gerard T. Hooft proposed that this idea might apply not just to black holes but to the entire universe. Imagine the cosmos as a vast hologram, where every particle, every force, and every event is encoded on a two-dimensional surface at the edge of reality. It's like a movie projected onto a screen where the three-dimensional images we see are just illusions created by the interplay of light and shadow. To make this concept more tangible, think of a credit card hologram, a flat surface that creates the illusion of depth when tilted. In a similar way, the holographic principle suggests that our three-dimensional reality might be a projection of information stored on a two-dimensional boundary. This boundary could be the edge of the universe itself, or perhaps something even more abstract like the event horizon of a black hole. But what does this mean for us? If the universe is a hologram, does that make our experiences less real? Not necessarily. The holographic principle doesn't deny the reality of our world. It simply offers a new way of understanding how that reality is constructed. It suggests that the fabric of the cosmos might be fundamentally informational, with the laws of physics emerging from the way this information is processed and projected. Leonard Susskind once said, "The holographic principle is not a theory of everything, but it's a principle that tells us something deep about the nature of reality." It's a reminder that the universe is far stranger and more interconnected than we often realize. And while the holographic principle is still a work in progress, it has already reshaped our understanding of space, time, and the very nature of existence. So, the next time you look up at the night sky, consider this. What if the stars above are not just points of light, but pixels in a cosmic hologram? each one encoding a piece of the universe's grand design. It's a thought that invites us to see the world in a new way, to question the nature of reality, and to marvel at the infinite possibilities hidden within the fabric of the cosmos. Is it possible for something to emerge from nothing? This question has puzzled philosophers, scientists, and thinkers for centuries. But what if the answer lies in the strange and unpredictable world of quantum physics? Enter quantum fluctuation theory, a bold idea that suggests the universe itself may have sprung from a random quantum event in what we might call nothingness. At its core, this theory challenges our understanding of reality, proposing that even in the emptiest void, the seeds of creation can emerge. To grasp this concept, we need to dive into one of the most fundamental principles of quantum mechanics, Heisenberg's uncertainty principle. This principle tells us that at the tiniest scales, the universe is never truly at rest. Instead, it's a seething, chaotic realm where particles and energy flicker in and out of existence like fleeting sparks in the dark. These momentary bursts of energy, known as quantum fluctuations, are not just theoretical, they've been observed in experiments and are a cornerstone of modern physics. Imagine a vast, empty ocean. Even on the calmest day, tiny ripples form on its surface, appearing and disappearing in an instant. In the same way, quantum fluctuations ripple through the fabric of reality, creating pockets of energy where, for a brief moment, something exists where there was once nothing. Now, take this idea a step further. What if one of these fluctuations was so significant that it sparked the birth of an entire universe? This is the essence of quantum fluctuation theory. Physicist Lawrence Krauss, one of the most vocal proponents of this idea, suggests that the universe could have emerged from a quantum event in a vacuum, a state we often think of as nothing. But here's the twist. According to quantum physics, a vacuum isn't truly empty. It's a seething cauldron of potential where particles and antiparticles constantly pop into existence and annihilate each other. Krauss famously described it as a boiling sea of virtual particles, a place where the rules of classical physics break down and the impossible becomes possible. Think of it like bubbles forming in a pot of boiling water. Each bubble represents a quantum fluctuation, a tiny burst of energy that could, under the right conditions, grow into something much larger. In the case of our universe, one of these bubbles may have expanded rapidly, setting off the chain reaction that led to the Big Bang. It's a mind-bending idea, but one that aligns with what we know about quantum mechanics and the behavior of energy at the smallest scales. This leads us to a deeper question: is nothingness truly empty? The answer, according to quantum fluctuation theory, is no. Even in the absence of matter and energy, the fabric of space-time is alive with potential, a dynamic arena where the laws of physics allow for spontaneous creation. It's a concept that challenges our everyday understanding of reality, forcing us to rethink what we mean by nothing. So, what does this mean for our understanding of the universe's origins? If quantum fluctuation theory is correct, it suggests that the cosmos may have emerged from a random event in a quantum vacuum, a process as natural and inevitable as the formation of raindrops in a storm. It's a humbling thought, one that reminds us of the profound interconnectedness of all things and the limitless potential hidden within the fabric of reality. As we ponder these ideas, we're left with more questions than answers. Could there be other universes born from similar fluctuations, each with its own unique set of physical laws? And if the universe can arise from nothing, does that mean it could happen again? These questions take us to the edge of our understanding, inviting us to explore the mysteries of existence with curiosity and wonder. The quantum fluctuation theory doesn't just explain the origins of the universe, it opens the door to a cosmos filled with infinite possibilities, each one waiting to be discovered. What if everything around us, the stars, the planets, even the thoughts in your mind, are nothing more than lines of code in an unimaginably advanced computer program. This is the startling premise of the simulation hypothesis, a theory that suggests our universe might not be the base reality, but a meticulously crafted simulation created by a civilization far more advanced than our own. It's an idea that blurs the line between science and philosophy, challenging us to rethink not just the nature of the cosmos, but the very essence of what it means to exist. The simulation hypothesis was popularized by philosopher Nick Bostrom, who argued that if a civilization could reach a level of technological sophistication capable of creating simulations indistinguishable from reality, it's statistically likely that we are living in one. Think about it. If a single advanced civilization could run countless simulations, the odds of us being in the original universe shrink dramatically. As Elon Musk famously put it, the odds that we're in base reality are 1 in billions. To make this idea more tangible, let's draw a parallel with video games. Imagine a game so realistic that the characters within it believe they're living in a real world, complete with emotions, memories, and free will. Now, imagine that same concept scaled up to the size of the universe, with every atom, every photon of light, and every thought being part of an intricate program. It's a mind-bending thought, but one that's rooted in the rapid progress of our own technology. Virtual reality, artificial intelligence, and even quantum computing are all steps toward a future where creating such simulations might be possible. The simulation hypothesis isn't just a sci-fi thought experiment, it has profound philosophical implications. If we are living in a simulation, what does that mean for consciousness? Is our sense of self an illusion, a byproduct of the code running the program? And what about free will? If every decision we make is predetermined by algorithms, do we truly have control over our lives? These questions take us to the heart of what it means to be human, blurring the boundaries between reality and illusion. Movies like The Matrix have explored these ideas in vivid detail, giving us a glimpse of what a simulated reality might look like. In the film, the protagonist Neo discovers that the world he knows is a computer-generated simulation designed to keep humanity docile. While The Matrix is fiction, it raises a compelling question. How would we know if we're living in a simulation? Some scientists suggest that glitches in the fabric of reality, tiny inconsistencies in the laws of physics, could be evidence of a simulated universe. Others propose that the very structure of space-time, with its discrete units and limits, might be hints of a digital foundation. But here's the twist: even if we are living in a simulation, does it really change anything? The world feels real to us, our experiences are meaningful, and the bonds we form with others are genuine. In that sense, perhaps it doesn't matter whether we're in a simulation or not. What matters is how we live our lives and the choices we make within the reality we inhabit. The simulation hypothesis invites us to think bigger, to question the nature of existence and our place within it. Whether we're lines of code in a vast cosmic program or beings in a base reality, the questions it raises are as profound as they are unanswerable. They challenge us to explore the boundaries of science, philosophy, and imagination, reminding us that the universe is far stranger and more wondrous than we often realize. So, the next time you look up at the stars or feel the warmth of the sun on your skin, consider this: what if it's all part of an elaborate simulation? And if it is, what does that mean for you, for me, and for the future of humanity? These questions don't just belong to scientists and philosophers, they belong to all of us. They invite us to dream, to wonder, and to explore the infinite possibilities of existence. What if the universe had no beginning and no end, a timeless, unchanging expanse that simply is? This is the essence of the steady-state theory, a bold and elegant idea that once stood as a rival to the Big Bang. Unlike the explosive birth of the cosmos we've come to accept, the steady-state theory proposes a universe that has always existed, eternal and unchanging, with no singular moment of creation. It's a concept that challenges our instinct to look for beginnings and endings, inviting us to imagine a cosmos that defies the very notion of time itself. At the heart of this theory is a simple yet profound idea. The universe maintains a constant density by continuously creating matter. Imagine a river that flows endlessly, its waters always full, never drying up. In the same way, the steady-state universe replenishes itself, with new particles of matter appearing out of the void to balance the expansion of space. This process, known as continuous creation, ensures that the universe remains uniform and unchanging on the largest scales, no matter how far we look into the cosmos. The steady-state theory was championed by some of the brightest minds in astronomy, including Fred Hoyle, who famously coined the term Big Bang as a dismissive label for the competing theory. Hoyle and his colleagues argued that the universe didn't need a fiery beginning. It could simply exist, eternal and self-sustaining. For a time, this idea captured the imagination of scientists and the public alike, offering an alternative to the Big Bang's dramatic narrative of creation. But how does this theory hold up against what we know today? The steady-state model faced its greatest challenge with the discovery of the cosmic microwave background radiation in the 1960s. This faint glow, the afterglow of the Big Bang, was a smoking gun for an explosive origin. It suggested that the universe wasn't eternal and unchanging, but rather had a fiery beginning and has been evolving ever since. Over time, as more evidence piled up in favor of the Big Bang, the steady-state theory fell out of favor, becoming a fascinating footnote in the history of cosmology. Yet the steady-state theory remains a captivating idea, one that pushes us to question our assumptions about the nature of the universe. Could it be that the cosmos has no true beginning, no moment of creation, but simply exists in an eternal state of balance? What would it mean for our understanding of time, of existence, if the universe had no start and no end? These questions don't just belong to the past, they continue to inspire curiosity and debate among scientists and thinkers today. The steady-state theory also reminds us that science is a journey, not a destination. It's a process of exploring ideas, testing them against evidence, and being willing to let go of even the most elegant theories when they no longer fit the facts. In that sense, the steady-state theory isn't just a relic of the past, it's a testament to the power of human imagination and the relentless pursuit of understanding. So, as we reflect on the steady-state universe, let's ask ourselves, what can this idea teach us about the nature of existence? Even if the theory itself has been discredited, it challenges us to think beyond the boundaries of what we know, to imagine a cosmos without beginnings or endings. It's a reminder that the universe is full of mysteries, and that every answer we find only leads to more questions. And in that endless seeking, we discover not just the secrets of the cosmos, but the boundless potential of our own curiosity. Picture this: two vast, invisible sheets floating in an unseen dimension, drifting closer and closer until crash. They collide in an explosion of energy so immense it births an entire universe. This is the dramatic vision at the heart of the Ecpyrrotic universe theory, a bold and captivating idea that reimagines the Big Bang not as a singular event, but as the result of a cosmic collision. The Ecpyrrotic model, proposed by physicists Paul Steinhardt and Neil Turok, suggests that our universe emerged from the collision of two branes short for membranes existing in a higher dimensional space. Imagine two sheets of paper floating parallel to each other in a room you can't see. When these branes collide, the energy released triggers a massive expansion, creating the conditions for a universe like ours. It's a theory that doesn't just explain the Big Bang. It offers an alternative to the inflationary model we've discussed earlier, proposing a different origin story for the cosmos. But what are these branes exactly? In string theory, branes are multidimensional objects that exist in higher dimensional spaces. Our universe in this framework could be likened to a three-dimensional brane floating in a higher dimensional bulk. When two branes collide, the energy from that impact gets funneled into our universe, setting off the rapid expansion we associate with the Big Bang. It's like the universe is a ripple on the surface of a pond, created by the splash of two stones colliding. The Ecpyrrotic model doesn't stop there. It also introduces the idea of cyclic brane collisions, suggesting that this isn't a one-time event. Instead, the branes might oscillate, pulling apart and colliding again in a never-ending cycle. Each collision triggers a new Big Bang, creating a universe that expands, cools, and evolves before the cycle repeats. This concept ties back to the cyclic universe model we explored earlier, but with a twist. The collisions themselves are the driving force behind the universe's rebirth. What's fascinating about this theory is how it addresses some of the lingering mysteries of the Big Bang. For example, the Ecpyrrotic model naturally explains why the universe is so uniform on a large scale. When the branes collide, the energy is distributed evenly, creating a smooth, homogeneous universe. It also sidesteps the singularity problem, that point of infinite density where our understanding of physics breaks down. Instead of a single, inexplicable origin, the universe emerges from a collision that, while unimaginably powerful, still operates within the bounds of physical laws we can, in theory, understand. But here's the question that lingers: could our universe be the result of a cosmic accident? If the Ecpyrrotic model is correct, then the birth of everything we know might have been a chance event, a random collision in a higher dimensional space. It's a humbling thought, one that challenges our instinct to look for purpose or design in the cosmos. At the same time, it opens up a world of possibilities. Are there other universes out there, born from their own brane collisions? Could our universe be just one in an endless sea of cosmic ripples? The Ecpyrrotic universe theory doesn't just reshape our understanding of the Big Bang, it invites us to think beyond the limits of our three-dimensional world. It's a reminder that the cosmos might be far more complex and interconnected than we ever imagined, with dimensions and realities we can't yet perceive. As we explore these ideas, we're not just uncovering the secrets of the universe's origins, we're pushing the boundaries of what it means to understand reality itself. So, the next time you look up at the night sky, consider this. What if the stars above are the aftermath of a collision between two invisible worlds, a cosmic event so vast it gave birth to everything we know? It's a thought that challenges us to see the universe in a new light, to wonder about the hidden dimensions that might lie just beyond our reach, and to keep searching for answers in the infinite expanse of the cosmos. What if the universe isn't just a random collection of particles and forces, but a finely tuned machine, perfectly calibrated to allow life to exist? This is the central idea behind the Anthropomorphic Principle, a concept that suggests the universe's fundamental constants, like the strength of gravity, the charge of an electron, or the speed of light, are set just right to make life possible. It's as if the cosmos has been carefully balanced on a razor's edge, with even the slightest change rendering it lifeless. The Anthropomorphic Principle comes in two flavors, the weak and the strong. The weak version is more of a statistical observation. It simply states that we observe the universe the way it is because, if it were any different, we wouldn't be here to see it. Think of it like this: if you're holding a winning lottery ticket, it's not because the universe favors you, it's because if you hadn't won, you wouldn't be holding the ticket at all. In the same way, the conditions of our universe might seem special, but only because we're here to witness them. The strong Anthropomorphic Principle, on the other hand, takes this idea a step further. It suggests that the universe must have properties that allow life to emerge. This version hints at something deeper, perhaps even a cosmic purpose or design. Physicist Brandon Carter, who first coined the term in the 1970s, argued that the universe's constants aren't random, they're fine-tuned to support conscious observers like us. To put this in perspective, imagine a radio dial with countless settings. Each knob controls a fundamental constant, like the strength of gravity or the mass of a proton. If any of these dials were turned even slightly, the universe as we know it would collapse. Stars wouldn't form, atoms wouldn't bond, and life would be impossible. It's as if someone or something set the dials to just the right positions, creating a universe where life could flourish. Stephen Hawking once mused on this idea, suggesting that the universe's fine-tuning might be evidence of a multiverse. In this scenario, our universe is just one of countless others, each with its own set of physical constants. Most of these universes would be barren, but in a few, the conditions would be just right for life to emerge. In that case, we're not special, we're just the lucky inhabitants of one of the rare universes where life is possible. But this raises a profound question. Is the universe designed for us, or are we simply the result of cosmic chance? Some see the Anthropomorphic Principle as evidence of a deeper purpose, a sign that the universe was crafted with life in mind. Others argue that it's just a matter of probability. If there are infinite universes, one of them had to be the right one. The Anthropomorphic Principle doesn't just challenge our understanding of the universe, it challenges our understanding of ourselves. Are we the result of a grand design or the product of random chance? And if the universe is fine-tuned for life, what does that mean for our place within it? These questions don't just belong to physicists, they belong to all of us. They invite us to reflect on the nature of existence and our role in the cosmos, reminding us that the universe is full of mysteries waiting to be explored. So the next time you look up at the stars, consider this. The universe might not just be a vast, indifferent expanse. It could be a finely tuned stage set for the emergence of life and for the story of consciousness itself. Whether by design or by chance, the fact that we're here to ask these questions is a mystery worth pondering. Ancient cultures across the world have long told stories of creation, often describing the universe as emerging from a single primordial source. One of the most enduring symbols of this idea is the cosmic egg, a metaphor for the universe's birth, representing a self-contained origin point from which all existence unfurls. It's a concept that feels almost poetic, yet it resonates deeply with one of the most profound ideas in modern science, the Big Bang's singularity. Today, we're diving into the cosmic egg theory, a fascinating blend of ancient wisdom and cutting-edge cosmology that invites us to reimagine the universe's origins. The cosmic egg theory, rooted in myths from Hindu, Egyptian, and Chinese traditions, envisions the universe as emerging from a single, self-contained entity. In these stories, the egg symbolizes both the potential for creation and the mystery of what lies within. Fast forward to the 20th century, and this ancient idea found new life in the work of physicist George Gamow, who played a pivotal role in developing the Big Bang theory. Gamow and his colleagues proposed that the universe began as an infinitely dense, hot point, a cosmic egg, if you will, that expanded and cooled over billions of years. To put this into perspective, imagine a single egg sitting in the void. Inside, there's no space, no time, no matter, just pure potential. Then, in a single, explosive moment, the egg cracks open, releasing the energy and matter that will eventually form stars, planets, and galaxies. This is the essence of the cosmic egg theory, a vivid way to visualize the singularity that gave rise to the universe. It's not just a metaphor, it's a bridge between the intuitive wisdom of ancient cultures and the rigorous science of modern cosmology. But what does it mean to say the universe began as a singularity? In physics, a singularity is a point where the laws of nature break down, a place where density and temperature become infinite, and our understanding of reality reaches its limits. It's a concept that challenges our imagination, yet it's central to the Big Bang theory. The cosmic egg theory doesn't just describe this moment, it frames it as a natural, almost organic process like the hatching of an egg. This perspective invites us to see the universe not as a cold, mechanical system, but as something alive, dynamic, and full of potential. So, what might lie inside the cosmic egg? If the universe began as a singularity, could there have been something before it, some kind of cosmic seed waiting to burst forth? These questions push the boundaries of our understanding, challenging us to think beyond the limits of time and space. They also remind us that the universe's origins are as much a philosophical mystery as they are a scientific one. The cosmic egg theory doesn't just offer a way to visualize the Big Bang. It connects us to a deeper, more intuitive understanding of creation. It's a reminder that the universe's story is one of transformation, from a single, concentrated point to the vast, intricate cosmos we see today. As we explore these ideas, we're not just uncovering the secrets of the universe's beginnings, we're rediscovering the timeless human impulse to make sense of the world around us. Whether you see the cosmic egg as a metaphor or a scientific concept, it's an idea that invites wonder and curiosity. It challenges us to think about the universe not just as a collection of particles and forces, but as a story, one that began with a single, unimaginable moment and continues to unfold with every passing second. And as we ponder the mysteries of the cosmic egg, we're reminded that the universe is far more than the sum of its parts. It's a living, evolving tapestry, woven from the threads of time, space, and imagination. What happens when the laws of physics as we know them break down? This is the question that drives the search for a theory of quantum gravity, an idea that seeks to unite the two great pillars of modern physics, quantum mechanics and general relativity. Quantum mechanics governs the behavior of the smallest particles, like electrons and quarks, while general relativity describes the vast cosmic dance of planets, stars, and galaxies. But when it comes to understanding the universe's earliest moments, or the extreme conditions inside a black hole, these two theories clash, leaving us with a puzzle that has stumped scientists for decades. Enter quantum gravity theories, a bold attempt to bridge this gap and explain the fundamental nature of reality. One of the leading contenders is loop quantum gravity, a framework developed by physicists like Carlo Rovelli and Lee Smolin. Imagine spacetime not as a smooth, continuous fabric, but as a tapestry woven from tiny, indivisible threads, loops of quantum energy. These loops form a network, creating the structure of spacetime itself. It's a radical reimagining of reality, one that suggests the universe might be made of discrete, quantized units, much like pixels on a screen. This idea has profound implications for the singularity problem, that mysterious point of infinite density where general relativity breaks down. In loop quantum gravity, the singularity isn't a true point at all. Instead, it's a quantum bridge, a moment where the fabric of spacetime folds back on itself, preventing the universe from collapsing into infinity. It's as if the universe hit a cosmic speed bump, bouncing back rather than breaking apart. This could mean that the Big Bang wasn't the beginning, but a transition from a previous state, a universe that existed before ours. Another approach to quantum gravity comes from string theory, which we've touched on earlier. String theory proposes that the fundamental building blocks of reality aren't particles, but tiny, vibrating strings. These strings exist in higher dimensions, weaving together the fabric of spacetime in ways we're only beginning to understand. Think of it like a cosmic symphony, where every string plays a unique note, creating the harmony of the universe. But what does this mean for the nature of spacetime? At the quantum level, spacetime might not be smooth and continuous as Einstein envisioned. Instead, it could be grainy, like the surface of a basketball when viewed up close. This granularity becomes significant at the smallest scales, where quantum effects dominate. It's a concept that challenges our everyday experience, reminding us that the universe operates in ways that often defy intuition. Physicists like Ravelli and Smolin have spent decades exploring these ideas, pushing the boundaries of what we know about the cosmos. Their work isn't just about solving equations, it's about redefining our understanding of space, time, and existence itself. And while quantum gravity remains a work in progress, it represents one of the most ambitious attempts to answer the deepest questions in science. So, what happens to spacetime at the quantum level? Is it a fabric woven from loops, a symphony of vibrating strings, or something even stranger? These questions don't just belong to physicists, they invite all of us to rethink the nature of reality. As we explore these ideas, we're reminded that the universe is far more mysterious and interconnected than we often realize. The search for quantum gravity isn't just a scientific pursuit, it's a journey into the heart of existence itself. And as we continue this journey, we're left with one final thought. What if the key to understanding the cosmos lies not in the extremes of the very large or the very small, but in the delicate balance between them? Quantum gravity offers a tantalizing glimpse into that balance, a bridge between the microscopic and the cosmic, the known and the unknown. It's a reminder that the universe, in all its complexity, is still waiting to reveal its secrets. What if our universe wasn't born from a single, fiery explosion, but from the collapse of a star in another reality? This is the intriguing premise of the black hole genesis theory. A bold idea that suggests the Big Bang might have been the result of a massive star collapsing into a black hole in another universe. It's a concept that turns our understanding of creation on its head, proposing that black holes aren't just cosmic vacuum cleaners, they could be the birthplaces of entirely new universes. At the heart of this theory is the idea that black holes might function as cosmic wombs, where the intense gravitational forces crush matter and energy into an infinitely dense point, only to give rise to something entirely new. Imagine a star in another universe, its core collapsing under its own weight, forming a black hole so dense that it warps the fabric of space-time. But instead of everything being lost forever, the energy and matter inside could be funneled into a new reality, a baby universe expanding rapidly like the one we inhabit today. Physicist Nikodem Poplawski is one of the leading voices behind this idea. In his work, he suggests that the singularity at the center of a black hole, the point where our laws of physics break down, might not be a dead end but a bridge to another universe. Think of it like a cosmic tunnel where the collapse of one star becomes the seed for a new universe. This theory elegantly connects black hole physics to cosmology, offering a fresh perspective on how universes might be born. To make this concept more relatable, let's use an analogy. Picture a black hole as a cosmic seed buried deep in the soil of another universe. When the conditions are right, that seed germinates, giving rise to a new universe that grows and expands, much like a plant sprouting from the earth. In this scenario, black holes aren't just destructive forces, they're creators, playing a vital role in the cosmic cycle of birth and renewal. But how does this connect to the Big Bang? According to the black hole genesis theory, the rapid expansion we associate with the Big Bang could have been triggered by the collapse of a star in another universe. The energy released during this collapse would have been funneled into our universe, setting off the chain reaction that led to the formation of stars, galaxies, and ultimately, life. It's a fascinating idea, one that suggests our universe might be just one link in an infinite chain of universes, each born from the collapse of a star in another reality. This theory also raises some mind-bending questions. Could black holes be gateways to other universes? If so, what lies on the other side? And if our universe was born from a black hole in another reality, does that mean there are other universes being born from black holes in ours? These questions push the boundaries of our imagination, challenging us to think beyond the limits of space and time. The black hole genesis theory doesn't just offer a new explanation for the Big Bang, it reshapes our understanding of the cosmos. It suggests that black holes might be more than just the end point of a star's life. They could be the starting point for something entirely new. As we explore these ideas, we're reminded that the universe is full of surprises, each one more astonishing than the last. So the next time you think about black holes, consider this. They might not be cosmic dead ends, but portals to new realities. What if every black hole is a doorway to another universe, a place where the laws of physics are different and the possibilities are endless? It's a thought that invites us to see the cosmos in a new light, to wonder about the hidden connections that bind us to other realities, and to keep searching for answers in the infinite expanse of the universe. What if gravity isn't the dominant force shaping the cosmos, but just one player in a much larger cosmic drama? This is the bold claim of the plasma universe theory, a revolutionary idea that suggests electromagnetism, not gravity, might be the true architect of the universe. Imagine a cosmos crisscrossed by vast electric currents where plasma, a superheated, electrically charged gas, shapes galaxies, stars, and even the vast cosmic voids between them. It's a vision of the universe that challenges everything we thought we knew about how it works. At the heart of this theory is plasma, often called the fourth state of matter. Unlike solids, liquids, or gases, plasma is made up of charged particles that can conduct electricity and generate magnetic fields. In fact, plasma makes up more than 99% of the visible universe, from the fiery surface of the Sun to the glowing filaments of distant nebulae. The plasma universe theory suggests that these charged particles don't just exist passively. They actively shape the cosmos through electric currents and magnetic fields, creating structures on scales we're only beginning to understand. To bring this idea to life, picture the universe as a vast electric circuit. Galaxies might act like nodes in this circuit, connected by filaments of plasma that carry electric currents across unimaginable distances. These currents could generate magnetic fields strong enough to shape the birth of stars and the evolution of galaxies. It's as if the cosmos is a giant machine, powered not by gravity alone, but by the invisible forces of electromagnetism. This theory owes much to the pioneering work of Hans Alfvén, a Nobel Prize-winning physicist who laid the foundations of plasma physics in the 20th century. Alfvén argued that traditional cosmology, with its focus on gravity, was missing a crucial piece of the puzzle. He believed that electric and magnetic forces played a far greater role in shaping the universe than most scientists realized. His ideas, though controversial at the time, have inspired a growing number of researchers to explore the plasma universe theory and its implications. But how does this challenge our current understanding of the cosmos? Conventional cosmology sees gravity as the dominant force, pulling matter together to form galaxies and stars. The plasma universe theory, on the other hand, suggests that electromagnetism might be just as important, if not more so, in shaping the large-scale structure of the universe. For example, the vast filaments of galaxies we observe in the cosmos might not be the result of gravity alone, but of electric currents flowing through plasma, creating structures that resemble the branching patterns of a lightning bolt. This raises a fascinating question. Could electromagnetism hold the key to some of the universe's greatest mysteries? From the formation of galaxies to the behavior of black holes, the plasma universe theory offers a fresh perspective on phenomena that have puzzled scientists for decades. It's a reminder that the cosmos is far more complex and interconnected than we often realize, with forces at work that we're only beginning to understand. As we explore these ideas, we're left to wonder, what if the universe is more like a vast electrical network than a gravitational playground? What if the forces we can't see, electric currents and magnetic fields, are shaping the cosmos in ways we've only just begun to imagine? These questions don't just challenge our understanding of the universe, they invite us to see it in a whole new light, one where the invisible forces of electromagnetism might hold the answers to some of our deepest questions. The plasma universe theory isn't just a scientific idea, it's a call to rethink what we know about the cosmos. It reminds us that the universe is full of surprises, and that the forces shaping it might be far more dynamic and diverse than we ever imagined. As we continue to explore these mysteries, we're reminded that the story of the universe is still being written, and that every discovery brings us one step closer to understanding the true nature of reality. Imagine a universe that never stops growing, a cosmos where space itself is constantly stretching, birthing new regions faster than the speed of light. This isn't science fiction, it's the essence of eternal inflation, a theory that takes the idea of cosmic inflation and pushes it to its most extreme and fascinating conclusion. In this model, inflation isn't just a one-time event that kickstarted the Big Bang. It's an ongoing process, a relentless expansion that spawns new universes like bubbles in an infinite cosmic sea. At the core of eternal inflation is the idea that some regions of space continue to inflate indefinitely, while others pinch off into their own separate universes. Picture a pot of water boiling on a stove, with bubbles forming, rising, and popping on the surface. Each bubble represents a new universe, complete with its own unique set of physical laws and constants. Some bubbles might be like ours, with stars, planets, and the potential for life. Others could be wildly different, governed by laws of physics so alien they're beyond our imagination. This theory owes much to the groundbreaking work of physicist Andre Linde, who proposed that inflation isn't just a one-and-done event but a self-replicating process. According to Linde, quantum fluctuations in the inflating regions create pockets where inflation slows down, allowing matter and energy to coalesce into new universes. Meanwhile, the rest of space continues to expand, ensuring that the process never truly ends. It's a cosmic feedback loop where the act of creation fuels even more creation, leading to an infinite tapestry of universes, a multiverse. But what does this mean for our place in the cosmos? If eternal inflation is correct, our universe might be just one of countless others, each with its own unique history and properties. Some universes might have stronger gravity, making stars burn out faster. Others could have more dimensions or even different forms of matter that we can't begin to comprehend. The possibilities are as vast as the multiverse itself. One of the most intriguing questions eternal inflation raises is this: what lies beyond the edge of our inflating universe? If space is continually expanding, is there a boundary, or does it stretch on forever? And if there are other universes out there, could they be so different that they're unrecognizable to us? These questions push the boundaries of what we know, challenging us to think beyond the limits of our own reality. Eternal inflation isn't just a theory about the universe's origins, it's a story of endless possibility. It suggests that the cosmos is far richer and more dynamic than we ever imagined, with new universes being born all the time. And while we may never be able to see these other universes directly, the idea that they exist invites us to think bigger, to wonder about the infinite variety of realities that might be out there. As we ponder the implications of eternal inflation, we're reminded that the universe is full of surprises. Whether it's the idea of a multiverse or the possibility of other realities governed by different laws of physics, these theories challenge us to see the cosmos in a new light. They invite us to dream, to explore, and to keep asking questions about the nature of existence itself. After all, in a universe that never stops expanding, the journey of discovery is as infinite as the cosmos itself. What if the fabric of space-time isn't smooth and continuous, but instead a frothy, turbulent sea, constantly bubbling with energy and activity? This is the essence of the quantum foam theory, a mind-bending idea that challenges our everyday understanding of reality. At the tiniest scales, space-time isn't the calm, unbroken surface we imagine. It's more like a stormy ocean, rippling with fluctuations so rapid and chaotic that particles pop in and out of existence in the blink of an eye. This theory arises from the strange and counterintuitive world of quantum mechanics, where nothing is ever truly at rest. Even in a vacuum, empty space isn't empty, it's alive with virtual particles, fleeting bursts of energy that appear and disappear faster than we can measure. These particles are like the bubbles in a boiling pot of water, constantly forming and vanishing in a dance governed by the uncertainty principle. Add gravity into the mix as described by general relativity, and you get quantum foam, a seething, dynamic froth where the very fabric of space-time is in constant flux. The term quantum foam was coined by physicist John Wheeler, one of the most influential thinkers in modern physics. Wheeler envisioned space-time as a turbulent, frothy medium at the smallest scales, where the smooth geometry we're familiar with breaks down into a chaotic, unpredictable landscape. Imagine looking at the surface of a calm lake from a distance. It appears smooth and glassy, but up close you see the ripples, waves, and tiny bubbles that make up its true nature. In the same way, space-time might appear smooth on a large scale, but at the level of the Planck scale, the smallest meaningful unit of measurement, it's a bubbling, churning foam. What does this mean for the nature of reality? If space-time is frothy at its core, then the very foundation of the universe is built on uncertainty. The smooth, predictable world we experience might be an illusion, a kind of cosmic averaging out of the chaos happening beneath the surface. It's as if the universe is a vast mosaic made up of countless tiny, unpredictable tiles that together create the appearance of order. This idea has profound implications for our understanding of the cosmos. For example, the quantum foam theory suggests that the singularity at the heart of a black hole or the Big Bang might not be a point of infinite density, but a region where space-time becomes so frothy and turbulent that our current laws of physics break down. It's a reminder that the universe is far stranger and more complex than we often realize, with layers of reality waiting to be uncovered. But here's the question that lingers. If space-time is a bubbling sea of energy, what does that mean for us? Does it change how we think about time, space, or even our own existence? These questions don't just belong to physicists, they invite all of us to reflect on the nature of reality and our place within it. The quantum foam theory isn't just a scientific idea, it's a window into the deepest mysteries of the cosmos, reminding us that the universe is full of surprises, each one more fascinating than the last. As we explore these ideas, we're reminded that the story of the universe is still being written. Whether space-time is smooth or frothy, predictable or chaotic, the journey of discovery is far from over. And in that journey, we find not just the secrets of the cosmos, but the endless potential of our own curiosity. What if the universe isn't a one-time event, but an eternal cycle of collapse and rebirth? This is the central idea behind the bouncing universe theory, a captivating model that suggests the cosmos doesn't end with a fiery collapse or fade into cold darkness. It rebounds like a cosmic phoenix rising from its ashes. Imagine a universe that contracts under its own gravity, collapsing into an unimaginably dense state, only to bounce back in a new Big Bang, starting the cycle all over again. It's a vision of the cosmos that turns the traditional Big Bang narrative on its head, offering a fresh perspective on the origins and possible future of everything we know. The bouncing universe theory proposes that the Big Bang wasn't the beginning of time, but a transition point in an endless cycle of expansion and contraction. According to this idea, the universe reaches a point where gravity pulls everything back together, leading to a big crunch, instead of ending in a singularity, a point of infinite density where the laws of physics break down. The universe rebounds, creating a new phase of expansion. It's like a ball bouncing on the ground. When it hits its lowest point, it doesn't stay there. It springs back up, ready to rise again. This theory isn't just a creative thought experiment, it's grounded in serious physics. Physicists like Martin Bojold have explored how quantum effects could prevent the universe from collapsing into a singularity. In his work, Bojold suggests that quantum mechanics could act like a cosmic cushion, softening the collapse and allowing the universe to rebound. Think of it as a safety net for the cosmos, ensuring that the universe doesn't end in a chaotic, physics-defying crunch, but instead transitions smoothly into a new cycle of expansion. One of the most intriguing aspects of the bouncing universe theory is the idea that the cosmos might retain some memory of its past cycles. Could the universe remember its previous incarnations, carrying forward traces of its history into the next cycle? This question pushes the boundaries of our understanding, challenging us to think about time, space, and existence in entirely new ways. To make this concept more tangible, let's use an analogy. Imagine a book with countless chapters, each one telling the story of a different universe. The end of one chapter, the big crunch, isn't the end of the story. It's just the beginning of the next chapter where the universe expands again, creating new stars, galaxies, and possibilities. In this analogy, the bouncing universe isn't just a single story, it's an epic saga, with each cycle adding a new layer to the cosmic narrative. But here's the question that lingers: what triggers the bounce? If the universe collapses under gravity, what force causes it to rebound? Some theories suggest that quantum effects, like the repulsion of particles at extremely high densities, could provide the necessary push. Others propose that the universe might transition through a phase where the laws of physics temporarily shift, allowing for the rebound. These ideas are still speculative, but they highlight the creativity and curiosity driving modern cosmology. The bouncing universe theory doesn't just offer a new way to think about the Big Bang. It invites us to imagine a cosmos that's dynamic, resilient, and endlessly renewing. It's a reminder that the universe might not have a single, definitive origin, but instead exists in a cycle of creation and destruction, birth and rebirth. As we explore these ideas, we're reminded that the story of the cosmos is far from over. It's a tale that's still being written, with each cycle adding a new chapter to the infinite book of the universe. So, the next time you look up at the night sky, consider this: could the universe be part of an eternal cycle, a cosmic heartbeat that pulses with the rhythm of expansion and contraction? It's a thought that challenges us to see the cosmos not as a static backdrop, but as a living, breathing entity full of surprises and possibilities. And in that vision, we find not just the mysteries of the universe, but the endless potential of our own curiosity. What if the universe isn't just a vast, indifferent expanse of stars and galaxies, but something far more profound, a living, thinking entity? This is the startling premise of the cosmic consciousness theory, an idea that suggests consciousness isn't just a product of the universe, but a fundamental part of it. Imagine the cosmos not as a cold, mechanical system, but as a vast, interconnected mind, aware of itself in ways we can barely comprehend. It's a concept that bridges the gap between quantum mechanics, neuroscience, and philosophy, challenging us to rethink what it means to exist in a universe that might be more alive than we ever imagined. At the heart of this theory is the idea that consciousness could be a basic property of the universe, like space, time, or energy. Just as gravity shapes the motion of planets and stars, consciousness might shape the very fabric of reality. This isn't just a philosophical musing. It's a hypothesis explored by some of the brightest minds in science. Physicist Roger Penrose and anesthesiologist Stuart Hameroff, for example, have proposed that consciousness arises from quantum processes in the brain, suggesting that the universe itself might operate on similar principles. To make this idea more tangible, let's use an analogy. Think of the universe as a vast brain with galaxies acting like neurons, connected by the cosmic web of dark matter and energy. Just as neurons communicate through electrical impulses, galaxies might exchange information through quantum connections, creating a network of consciousness that spans the cosmos. It's a breathtaking vision, one that suggests the universe isn't just a collection of objects, but a dynamic, thinking entity. But how could consciousness exist on such a grand scale? One possibility lies in the strange and unpredictable world of quantum mechanics. At the smallest scales, particles don't behave like solid objects. They exist in a state of probability, flickering in and out of existence like thoughts in a mind. Some scientists like Penrose and Hameroff suggest that these quantum processes might be the foundation of consciousness, both in our brains and in the universe as a whole. It's as if the cosmos itself is engaged in a constant conversation, its quantum thoughts shaping the reality we experience. This idea also raises profound questions about our place in the universe. If consciousness is a fundamental property of the cosmos, does that mean the universe is aware of us? Could it be observing itself through the eyes of living beings like us? These questions blur the line between science and philosophy, inviting us to consider the possibility that the universe isn't just a stage for life, but a participant in its own story. The cosmic consciousness theory doesn't just challenge our understanding of the universe, it challenges our understanding of ourselves. It suggests that our thoughts, feelings, and experiences might be part of a larger cosmic mind, connected to the fabric of reality in ways we're only beginning to explore. It's a humbling thought, one that reminds us of the profound interconnectedness of all things. As we ponder these ideas, we're left with more questions than answers. Could the universe be aware of itself, observing its own creation through the eyes of countless living beings? And if so, what does that mean for the nature of existence? These questions don't just belong to scientists or philosophers, they belong to all of us. They invite us to see the universe not as a cold, lifeless void, but as a living, thinking entity full of mysteries waiting to be uncovered. So the next time you gaze up at the night sky, consider this: what if the stars above are more than just points of light? What if they're part of a vast cosmic mind, thinking, feeling, and evolving in ways we can only begin to imagine? It's a thought that invites us to see the universe in a new light, to wonder about the infinite possibilities hidden within its depths, and to keep searching for answers in the endless expanse of the cosmos. What if the universe, in all its vast complexity, was born from nothing, a perfect balance of positive and negative energy that adds up to zero? This is the startling idea behind the zero-energy universe theory, a concept that suggests the cosmos might be the ultimate free lunch. At its core, this theory proposes that the positive energy contained in matter, light, and all the stars and galaxies is perfectly offset by the negative energy of gravity. The result, a universe that, on balance, contains zero energy. It's a thought that challenges our most basic assumptions about existence, suggesting that everything we see around us could have emerged from nothing at all. To understand this idea, let's start with the concept of energy. In physics, energy is what makes things happen. It's the fuel that powers stars, moves planets, and lights up the night sky. But energy isn't just a one-way street. For every action, there's an equal and opposite reaction. And for every bit of positive energy, there's a corresponding negative energy. Gravity, the force that holds the universe together, is often described as having negative energy because it does work pulling objects together without adding energy to the system. When you add up all the positive energy in the universe and subtract the negative energy of gravity, you might just end up with zero. This idea isn't just a clever thought experiment. It's grounded in the work of some of the most brilliant minds in physics. Stephen Hawking, for example, explored the concept of a zero-energy universe in his book A Brief History of Time, suggesting that the universe could have emerged from a quantum fluctuation in a state of perfect balance. Alan Guth, the physicist behind the theory of cosmic inflation, also touched on this idea, proposing that the rapid expansion of the early universe could have been fueled by the interplay of positive and negative energy. To make this concept more relatable, think of the universe as a perfectly balanced equation. On one side, you have all the energy contained in matter, light, and motion, the stars, planets, and galaxies. On the other side, you have the negative energy of gravity pulling everything together. When you add them up, the total comes to zero. It's like taking out a loan to buy a house. The money you owe is balanced by the value of the house itself, leaving you with a net worth of zero. In the same way, the universe might be a cosmic balancing act, where the energy of creation is perfectly offset by the energy of its own structure. But here's the question that lingers. If the universe has zero energy, does that mean it could have come from nothing? The answer, according to this theory, is yes. In quantum mechanics, particles and energy can appear out of the vacuum of empty space, as long as they disappear quickly enough to balance the books. The zero-energy universe theory takes this idea to its ultimate conclusion, suggesting that the entire cosmos could have emerged as a quantum fluctuation, a momentary ripple in the fabric of nothingness that somehow became permanent. This raises another profound question. What is nothing? In quantum physics, a vacuum isn't truly empty. It's a seething cauldron of potential, where particles and energy flicker in and out of existence. The zero-energy universe theory suggests that even in this state of apparent emptiness, the seeds of creation are present, waiting for the right conditions to sprout into a full-blown universe. It's a reminder that the universe is far stranger and more interconnected than we often realize, with layers of reality waiting to be uncovered. As we explore these ideas, we're left with more questions than answers. Could the universe truly have emerged from nothing? And if so, what does that mean for the nature of existence? These questions don't just belong to physicists. They invite all of us to reflect on the mysteries of the cosmos and our place within it. The zero-energy universe theory isn't just a scientific idea, it's a philosophical journey, one that challenges us to rethink what we know about reality itself. So, the next time you look up at the night sky, consider this. The universe might not be a vast, unending expanse of energy and matter, but a perfect balance of forces, a cosmic equation that adds up to zero. It's a thought that invites us to see the cosmos in a new light, to wonder about the infinite possibilities hidden within its depths, and to keep searching for answers in the endless expanse of the universe. Picture the universe not as a random scattering of stars and galaxies, but as an intricate, sprawling web, a cosmic tapestry woven together by invisible threads of dark matter and gravity. This is the essence of the cosmic web theory, a framework that reveals the universe's large-scale structure in breathtaking detail. Instead of isolated islands of galaxies, the cosmos is a connected network, with galaxies clustered along filaments that stretch across unimaginable distances. These filaments intersect at nodes, creating vast clusters, while the spaces between them form enormous voids, regions of near nothingness that stretch for millions of light years. It's a structure both beautiful and mysterious, one that shows the universe as a living, dynamic entity, shaped by forces we're only beginning to understand. At the heart of this cosmic web lies dark matter, an invisible substance that makes up about 85% of the universe's mass. Though we can't see it directly, dark matter's gravitational pull acts like an unseen hand, sculpting the web's filaments and guiding the formation of galaxies. Gravity, the force that binds the cosmos together, draws matter into dense regions along these filaments, creating the clusters and superclusters we observe today. The result is a universe that resembles a spider's web on a monumental scale, with galaxies strung like dewdrops along its delicate strands. Cosmologists like J. Richard Gott have spent decades mapping this vast structure, using advanced telescopes and computer simulations to trace the web's intricate patterns. Their work has revealed a universe far more organized than we once imagined, with filaments stretching across billions of light years and connecting galaxies in a cosmic dance. To visualize this, think of the cosmic web as a network of rivers with galaxies flowing along the currents of gravity, gathering in pools at the intersections. The voids, then, are the empty spaces between these rivers, vast, silent expanses where little to no matter exists. But what lies within these voids? Are they truly empty, or do they hold secrets we've yet to uncover? Some scientists believe that voids could contain faint traces of dark energy, the mysterious force driving the universe's accelerated expansion. Others speculate that these regions might harbor isolated galaxies or even exotic forms of matter hidden from our view. Whatever the case, the voids remind us that the universe is full of mysteries, with every discovery leading to new questions. The cosmic web theory doesn't just explain the structure of the universe, it offers a glimpse into its evolution. From the first moments after the Big Bang, tiny fluctuations in density grew over billions of years, amplified by gravity to form the web we see today. It's a process both slow and inevitable, a testament to the power of gravity to shape the cosmos on the grandest scales. As we explore this idea, we're reminded that the universe is more than just a collection of stars and galaxies. It's a living, breathing network, constantly evolving and reshaping itself. The cosmic web invites us to see the cosmos in a new light, to marvel at its complexity, and to wonder about the forces that bind it together. Whether you're gazing at the night sky or pondering the mysteries of dark matter, the cosmic web reminds us that the universe is a story still being written one thread at a time. Let's take a step back and ask a question that seems almost impossible to answer. What happened before time began? It's a concept that stretches the limits of our imagination, a universe without a past, present, or future. For most of us, time feels like an unbroken thread, something that has always been there, ticking steadily forward. But what if time itself had a starting point? What if the Big Bang wasn't just the birth of the universe, but the moment time itself began to flow? This idea isn't just a philosophical musing, it's a serious scientific question. According to many cosmologists, time as we know it might have emerged alongside space and matter during the Big Bang. Before that, the concept of before may not even apply. Think of it like this: if time began with the Big Bang, asking what came before is like asking what's north of the North Pole. There's no frame of reference, no way to define what before means in a universe where time didn't yet exist. Physicist Sean Carroll has spent years exploring the nature of time, delving into the strange and counterintuitive world of cosmology. He suggests that time might not be a fundamental feature of the universe, but something that emerges from deeper, timeless laws. Imagine time as a river flowing steadily from the Big Bang onward. But if you trace that river back to its source, there's no riverbed, no water, just a point where the river begins. In the same way, time might emerge from a timeless state, a kind of cosmic blank slate where the rules of cause and effect don't yet apply. This raises a fascinating question: can we even imagine a state without time? For humans who are bound by the flow of seconds, minutes, and years, the idea of timelessness is almost incomprehensible. Yet, some theories suggest that the universe's earliest moments were so extreme that time, as we understand it, didn't exist. Instead, the cosmos might have existed in a state of pure potential, a quantum soup where events didn't happen in sequence but all at once. To make this concept more tangible, think of a movie. When you watch a film, the story unfolds frame by frame, moment by moment. But if you could pause the movie and look at every frame at once, the story would lose its sequence. It would just be a collection of still images. In a similar way, the universe before time might have been a collection of possibilities, a kind of cosmic pause where nothing happened because there was no time for events to unfold. But here's where it gets even more intriguing. If time began with the Big Bang, what does that mean for causality, the idea that every effect has a cause? In our everyday lives, causality feels like a fundamental truth, but in a timeless state, cause and effect might not exist in the way we understand them. Instead, the universe could have emerged from a set of conditions where the usual rules of physics simply didn't apply. As we explore these ideas, we're reminded that the universe is far stranger and more mysterious than we often realize. The concept of a timeless beginning challenges not just our understanding of time, but our very sense of what it means to exist. It invites us to think beyond the limits of our experience, to imagine a cosmos that operates on principles we can barely comprehend. So the next time you glance at a clock or watch the sun rise and set, consider this: time might not be an eternal, unchanging backdrop to the universe. It could be a feature that emerged from a deeper, more fundamental reality, a reality we're only beginning to understand. And as we continue to explore these mysteries, we're reminded that the universe is full of surprises, each one more fascinating than the last. Now, let's shift our focus to a phenomenon so strange and counterintuitive that even Albert Einstein called it spooky action at a distance. Imagine two particles separated by billions of light years, yet somehow instantly connected, as if they share a secret language that defies the limits of space and time. This is the essence of quantum entanglement, a mind-bending concept that suggests the universe is far more interconnected than we ever imagined. At its core, quantum entanglement is a phenomenon where two or more particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. It's as if these particles are cosmic twins, sharing an invisible bond that transcends the vast emptiness of space. This connection happens faster than the speed of light, challenging one of the fundamental principles of classical physics, that nothing can travel faster than light. Einstein famously struggled with this idea, calling it spooky because it seemed to violate the rules of causality, the idea that causes must precede effects. He believed that the universe operated on local realism, meaning that objects are only influenced by their immediate surroundings. But quantum entanglement suggests something far more profound, that the universe might be fundamentally non-local, with particles communicating instantaneously across vast distances. To make this concept more relatable, think of entangled particles as a pair of dice. If you roll one die and it lands on a 6, the other die, no matter where it is, will also show a 6. It's not magic. It's a fundamental property of the quantum world where particles exist in a state of superposition, meaning they can be in multiple states at once until they're observed. When one particle is measured, it instantly chooses a state, and its entangled partner does the same, even if they're galaxies apart. But what does this mean for our understanding of the universe? Quantum entanglement doesn't just challenge classical physics. It has profound implications for cosmology. Some scientists believe that entanglement could be the key to understanding the universe's unity, suggesting that everything from the smallest particles to the largest galaxies might be connected in ways we're only beginning to uncover. It's as if the cosmos is a vast, intricate web, with every thread tied together by the invisible bonds of quantum entanglement. This idea raises fascinating questions. Could entanglement explain the uniformity of the cosmic microwave background, the faint glow left over from the Big Bang? Might it hold clues about the nature of dark matter and dark energy, the mysterious forces shaping the universe's evolution? And if the universe is so deeply interconnected, what does that mean for our place within it? As we explore these questions, we're reminded that the universe is far stranger and more interconnected than we often realize. Quantum entanglement isn't just a scientific curiosity, it's a window into the fundamental nature of reality, inviting us to see the cosmos not as a collection of separate objects, but as a dynamic, unified whole. It's a reminder that even in the vast emptiness of space, nothing is truly alone, and every particle is part of a greater cosmic dance. So, the next time you look up at the night sky, consider this. What if the stars above are not just distant points of light, but part of an intricate, interconnected tapestry, woven together by the invisible threads of quantum entanglement? It's a thought that challenges us to see the universe in a new light, to wonder about the hidden connections that bind it together, and to keep searching for answers in the infinite expanse of the cosmos. Most of the universe's matter isn't just hidden, it's invisible. Stars, planets, and galaxies, dazzling as they are, make up less than 20% of the cosmos. The rest, it's something we can't see, touch, or even detect directly. This elusive substance, known as dark matter, doesn't emit light, absorb it, or interact with electromagnetic forces. Yet it's everywhere, shaping the very fabric of the universe in ways we're only beginning to understand. So, how do we even know dark matter exists if we can't observe it directly? The answer lies in its gravitational effects. Imagine watching leaves swirl in the wind. You can't see the air, but you know it's there because of how it moves the leaves. In the same way, dark matter reveals itself through its gravitational pull. Galaxies spin faster than they should based on the visible matter alone, and clusters of galaxies bend light in ways that defy explanation without the presence of something unseen. It's as if the universe is filled with invisible scaffolding, holding everything together. One of the key figures in uncovering this mystery was astronomer Vera Rubin. In the 1970s, Rubin studied the rotation curves of galaxies, measuring how fast stars orbit their centers. What she found was astonishing. Stars at the edges of galaxies were moving just as fast as those near the center, a phenomenon that couldn't be explained by the gravity of visible matter alone. Her work provided some of the strongest evidence for dark matter, fundamentally changing how we see the cosmos. Rubin's discoveries were a reminder that sometimes the most important truths are the ones we can't see. But what exactly is dark matter? Despite decades of research, we still don't know. It doesn't interact with light, making it invisible to telescopes. It doesn't collide with ordinary matter, passing through it like a ghost, and yet it makes up about 85% of the universe's total matter. Scientists have proposed various candidates, from weakly interacting massive particles WIMP to actions, hypothetical particles that could explain dark matter's behavior. But so far, none have been definitively detected. The search for dark matter is one of the most exciting challenges in modern physics. Experiments deep underground, in space, and at particle accelerators are all hunting for clues. Some scientists are even looking for tiny flashes of light that dark matter might produce when it interacts with special materials. It's a bit like trying to catch a shadow. You know it's there, but it's incredibly hard to pin down. This raises a deeper question. If dark matter is so pervasive, why can't we see it? The answer might lie in the very nature of the universe. Just as fish might not recognize the water they swim in, perhaps dark matter is so fundamental to the cosmos that it's woven into the fabric of reality itself. It's a humbling thought, one that reminds us how much we still have to learn about the universe. As we continue to explore the mystery of dark matter, we're reminded that the cosmos is full of surprises. Every discovery brings us closer to understanding the invisible forces that shape our universe, from the smallest particles to the largest galaxies. And while the answers remain elusive, the journey itself is a testament to the boundless curiosity and ingenuity of the human spirit. So, the next time you gaze at the night sky, consider this. The stars and galaxies you see are just the tip of the cosmic iceberg. Hidden in the darkness is a vast, invisible realm, shaping the universe in ways we're only beginning to uncover. It's a mystery that invites us to keep searching, keep questioning, and keep dreaming about the infinite possibilities that lie beyond the edge of what we can see. Imagine this: the universe isn't just expanding, it's speeding up, racing into the unknown at an ever-increasing pace. This startling discovery, made in the late 1990s, completely reshaped our understanding of the cosmos. For decades, scientists believed that the universe's expansion was slowing down, pulled back by the relentless tug of gravity. But when astronomers like Saul Perlmutter and his team observed distant supernova, they found something extraordinary. The light from these exploding stars was fainter than expected, suggesting they were farther away than they should have been. The only explanation: the universe wasn't just expanding, it was accelerating. This revelation led to the introduction of one of the most mysterious concepts in modern physics: dark energy. Unlike dark matter, which pulls galaxies together, dark energy acts as a kind of cosmic repellent, pushing space itself apart. Think of it as an invisible engine constantly revving up the expansion of the universe. But here's the twist: we don't know what dark energy is. It doesn't emit light, interact with matter, or leave any direct trace we can detect. Yet, it makes up about 68% of the universe's total energy content, dwarfing everything else we know. To understand how strange this is, let's compare the universe to a car. If gravity is the brake, slowing things down, dark energy is the accelerator, pressing down harder and harder. Over time, the brakes lose their grip and the car speeds up, racing away faster and faster. But in this case, the car is the entire universe and the road is the fabric of space-time. It's a mind-bending idea, one that challenges our understanding of gravity, energy, and the very nature of reality. The discovery of dark energy didn't just earn Saul Perlmutter and his colleagues the Nobel Prize. It fundamentally changed the way we think about the universe's fate. If dark energy continues to dominate, the universe could keep expanding forever, growing colder and emptier as galaxies drift apart. In this scenario, known as the Big Freeze, the cosmos would become a vast, dark wasteland, with stars burning out and matter spread so thin that even atoms might eventually unravel. But there's another, more dramatic possibility. If dark energy grows stronger over time, it could tear the universe apart in a catastrophic event called the Big Rip. Picture space itself stretching until galaxies, stars, and even atoms are ripped to shreds. So, what could dark energy be? One leading theory is that it's a property of space itself, often referred to as the cosmological constant. This idea dates back to Albert Einstein, who introduced the concept to explain a static universe, a notion he later abandoned. But modern cosmologists have revived it, suggesting that empty space might have an inherent energy that drives expansion. Another possibility is that dark energy is a new kind of field, similar to the Higgs field, but with properties we've yet to uncover. The mystery of dark energy isn't just a scientific puzzle, it's a reminder of how much we still have to learn about the cosmos. It challenges us to rethink our most fundamental assumptions, from the nature of gravity to the ultimate fate of the universe. And as we explore these questions, we're reminded that the universe is full of surprises, each one more fascinating than the last. What does dark energy mean for us? Could it one day tear the universe apart, or will it simply fade into the background, leaving the cosmos to expand quietly into eternity? These questions don't just belong to physicists, they invite all of us to reflect on the mysteries of existence and our place within the universe. As we continue to explore the enigma of dark energy, we're reminded that the universe is far more dynamic and mysterious than we often realize. And in that mystery lies the endless potential of discovery. Imagine holding a photograph of the universe when it was just a baby, a snapshot taken moments after its birth, capturing the first light to ever travel through space. This isn't science fiction, it's the cosmic microwave background, or CMB, the oldest light in the universe and one of the most profound pieces of evidence we have for the Big Bang. Often described as the afterglow of creation, the CMB is a faint glow of microwave radiation that permeates every corner of the cosmos, a relic from a time when the universe was just 380,000 years old. So, what exactly is the CMB? To understand it, let's rewind the cosmic clock. In the early universe, everything was a seething, opaque soup of particles and energy. Light couldn't travel far without bumping into something, making the universe as impenetrable as a dense fog. But as the universe expanded and cooled, electrons and protons combined to form neutral atoms, allowing light to travel freely for the first time. This moment, known as recombination, released a burst of radiation that has been traveling through space ever since. Over billions of years, that light has stretched and cooled, shifting from visible wavelengths to microwaves, what we now detect as the CMB. The discovery of the CMB is a story of curiosity and serendipity. In the 1960s, physicists Arno Penzias and Robert Wilson were working with a sensitive radio antenna in New Jersey, trying to eliminate a persistent hiss of static that seemed to come from everywhere in the sky. After ruling out everything from pigeon droppings to equipment malfunctions, they realized they'd stumbled upon something extraordinary, the faint echo of the Big Bang itself. Their discovery earned them the Nobel Prize and provided the first solid evidence for the Big Bang theory, transforming our understanding of the universe's origins. Think of the CMB as a cosmic fossil, a remnant of the universe's fiery infancy. Just as fossils give us insights into ancient life, the CMB offers a glimpse into the early universe, revealing its temperature, density, and composition. The temperature of the CMB is remarkably uniform, about 2.7 degrees above absolute zero, but it's not perfectly smooth. Tiny fluctuations in the CMB's temperature, less than 100,000th of a degree, tell a story of the seeds of structure in the universe. These fluctuations are the blueprint for everything we see today, the tiny ripples that would grow into galaxies, stars, and planets over billions of years. But the CMB isn't just a snapshot of the past. It's also a treasure trove of information about the universe's evolution. By studying these tiny temperature variations, scientists have been able to measure the age of the universe, estimate its composition, and even uncover clues about the mysterious forces of dark matter and dark energy. It's like piecing together a cosmic puzzle where every detail reveals a new layer of the story. What secrets does the CMB hold about the universe's origins? Could it reveal clues about what happened in the first moments after the Big Bang, or even before it? These are the questions that drive cosmologists to study this ancient light, pushing the boundaries of our understanding. The CMB reminds us that the universe is not just a collection of stars and galaxies, but a dynamic, evolving entity with a history written in light. As we explore the mysteries of the CMB, we're reminded of how far we've come in understanding the cosmos and how much further we have to go. It's a testament to the power of curiosity, collaboration, and the relentless pursuit of knowledge. And as we continue to unravel the story of the universe, we're left with one final thought. What other secrets are hidden in the echoes of the Big Bang waiting to be discovered? Let's rewind the clock to a time when the universe wasn't filled with galaxies, stars, or even atoms, just a seething, chaotic sea of energy and particles. This is the primordial soup, a state so hot and dense that matter and energy were indistinguishable, swirling together in a cosmic cauldron. It's hard to imagine now, but in these earliest moments, the universe was more like a boiling pot of water than the structured cosmos we see today. Every particle, every bit of energy was part of this fiery mix, colliding and interacting in ways that would eventually give rise to everything we know. At the heart of this primordial soup was an extraordinary balance of forces. Protons, neutrons, and electrons, the building blocks of matter, were constantly forming and breaking apart, unable to stabilize in the extreme heat. Photons, the particles of light, zipped through this dense environment, colliding with matter so frequently that the universe was essentially opaque. It was a world without structure, without form, but filled with the raw potential for creation. Enter George Gamow, a physicist whose work helped unravel the mysteries of this early universe. Along with his colleagues Ralph Alpher and Robert Herman, Gamow explored how the primordial soup cooled and transformed over time. As the universe expanded, it also cooled, allowing particles to combine in new ways. Within minutes, protons and neutrons began to fuse, forming the first atomic nuclei. This process, known as nucleosynthesis, gave birth to the lightest elements: hydrogen, helium, and traces of lithium. These elements became the building blocks of stars, planets, and ultimately, life itself. To visualize this, think of the primordial soup as a cosmic kitchen. Imagine throwing all the ingredients for a meal into a pot and turning up the heat. At first, everything is chaotic, a bubbling, swirling mess. But as the pot cools, the ingredients begin to settle, forming new combinations and structures. In the same way, the early universe started as a chaotic mix of energy and particles. But as it expanded and cooled, it began to take shape, creating the first elements that would eventually form galaxies and stars. This raises a fascinating question: how did the universe's first ingredients form? The answer lies in the delicate balance of forces at play. Gravity, the force that pulls matter together, was competing against the rapid expansion of space itself. As the universe cooled, gravity began to gain the upper hand, pulling particles into clumps that would eventually grow into stars and galaxies. It's a process that took billions of years, but it all started in that primordial soup where the universe's first building blocks were forged. The work of Gamow and his team didn't just explain the origins of the elements, it gave us a glimpse into the universe's earliest moments. By studying the primordial soup, we can trace the cosmic recipe that led to the formation of everything we see today. It's a reminder that the universe, in all its complexity, began as a simple, chaotic mix of energy and particles, a cosmic cauldron filled with infinite potential. As we explore these ideas, we're reminded of the profound interconnectedness of all things. The elements that make up our bodies, the stars in the night sky, and the galaxies stretching across the cosmos, all of it traces back to that primordial soup. It's a story that invites us to marvel at the beauty of creation, to wonder about the forces that shaped the universe, and to keep searching for answers in the endless expanse of the cosmos. So, the next time you look up at the stars, consider this: you're not just looking at distant points of light. You're seeing the remnants of a cosmic kitchen, where the universe's first ingredients were cooked up billions of years ago. It's a thought that connects us to the very beginnings of existence, reminding us that we are all part of a story that began long before we were here, a story that continues to unfold with every passing moment. Picture a universe shrouded in darkness, a vast, empty expanse where no stars or galaxies yet exist. This was the cosmos just a few 100 million years after the Big Bang, a time known as the Cosmic Dark Ages. But then, something extraordinary happened. The first stars ignited, piercing the darkness like cosmic beacons. These weren't just any stars, they were the universe's first true light, blazing into existence and forever changing the course of cosmic history. This pivotal moment marked the beginning of the era of reionization, a transformative period when the first stars and galaxies began to form, lighting up the universe and setting the stage for everything that followed. These first stars, often called population Roman III stars, were unlike anything we see today. Imagine a star so massive and luminous that it outshines entire galaxies. These stars were hundreds of times more massive than our Sun, made almost entirely of hydrogen and helium, the only elements available in the early universe. Their intense radiation ionized the surrounding gas, stripping electrons from atoms and creating the first pockets of transparency in the once opaque cosmos. It's as if the universe was waking up from a long, dark slumber, flickering to life one star at a time. But how did these stars form in the first place? In the early universe, gravity pulled together the first clumps of gas, compressing them until they reached temperatures hot enough to trigger nuclear fusion. This process, the same one that powers the Sun today, transformed the universe's raw ingredients into the first light and energy. These stars didn't just illuminate the cosmos, they also seeded it with the first heavy elements like carbon, oxygen, and nitrogen, forged in their cores and scattered across the universe when they exploded as supernova. Without these first stars, the building blocks of life as we know it wouldn't exist. Astronomers like Richard Ellis have spent decades studying this era, using powerful telescopes to peer back in time and catch glimpses of the universe's earliest light. Ellis and his colleagues have used observations from the Hubble Space Telescope and other instruments to piece together the story of these first stars, revealing how they transformed the cosmos. Their work shows that the era of reionization wasn't just a brief flash in the cosmic timeline, it was a profound and lasting shift, one that shaped the universe into the vibrant, star-filled expanse we see today. To help visualize this, think of the first stars as cosmic candles, flickering to life one by one in the darkness. Each star not only lit up its corner of the universe, but also created the conditions for more stars and galaxies to form. Over time, these stars gathered into clusters, forming the first galaxies and laying the foundation for the cosmic web we see today. It's a reminder that even the smallest light can illuminate the darkness, sparking a chain reaction that changes everything. So, what were these first stars like, and how did they shape the universe? They were the universe's pioneers, blazing a trail through the cosmic wilderness and leaving behind the elements that would one day form planets, oceans, and even life itself. Their story is a testament to the power of creation, a reminder that even in the darkest of times, light can find a way to shine. As we continue to explore the mysteries of the first stars, we're reminded of our own connection to the cosmos. The elements that make up our bodies, the air we breathe, and the ground beneath our feet were all forged in the hearts of stars that burned long ago. In that sense, we are all stardust, part of a story that began billions of years ago with the first flicker of light in the darkness. And as we look up at the night sky, we're not just gazing at distant stars, we're seeing the legacy of those first cosmic pioneers whose light still guides us today. Galaxies are the universe's great cities, vast, bustling metropolises of stars, planets, and cosmic activity. But how did these colossal structures come to be? The answer lies in the galaxy formation theory, a framework that explains how galaxies emerged from the intricate web of dark matter and gravity that shapes the cosmos. Picture the universe as a cosmic ocean with galaxies scattered like islands across its surface. Each galaxy is unique with its own shape, size, and story, yet all are connected by the invisible threads of the cosmic web. At the heart of this process is dark matter, the mysterious substance that makes up most of the universe's mass. Though invisible, dark matter's gravitational pull acts like a cosmic scaffold, drawing ordinary matter, gas, dust, and particles into dense clumps. Over billions of years, these clumps grew, collapsing under their own gravity to form the first galaxies. Gravity, the force that binds the cosmos together, continued to shape these structures, pulling galaxies into clusters and superclusters, creating the vast, interconnected network we see today. Cosmologists like Sandra Faber have spent decades studying this process, unraveling the mysteries of how galaxies evolve and grow. Faber's work has shown that galaxies aren't static, they're dynamic, ever-changing entities shaped by collisions, mergers, and the flow of gas and stars. Her research has revealed that galaxies come in a stunning variety of shapes and sizes, from the graceful spirals of the Milky Way to the chaotic ellipticals, formed by the violent collisions of smaller galaxies. To bring this idea to life, think of a galaxy as a cosmic ecosystem where stars are born, live, and die, enriching the galaxy with new elements. These elements, forged in the hearts of stars, are the building blocks of planets, comets, and even life itself. In this way, galaxies aren't just collections of stars, they're cosmic factories, constantly producing the raw materials that make the universe vibrant and diverse. But here's a question to ponder. What makes each galaxy unique? Is it the way it formed, the environment it inhabits, or the forces that continue to shape it? These questions remind us that galaxies, like cities, have their own histories and identities, shaped by the interplay of countless factors. As we explore the story of galaxy formation, we're reminded of the profound interconnectedness of the cosmos. Every galaxy, from the smallest dwarf to the largest supercluster, is part of a grand cosmic tapestry, woven together by the forces of gravity and dark matter. It's a story that invites us to marvel at the beauty and complexity of the universe and to keep searching for answers in the endless expanse of the cosmos. So, the next time you gaze at the night sky, consider this. Every galaxy you see is a testament to the universe's creativity, a masterpiece of cosmic architecture that began billions of years ago with the first flicker of light in the darkness. Each one holds secrets waiting to be uncovered, stories waiting to be told, and mysteries waiting to be explored. What if the universe itself is a cosmic recipe, perfectly calibrated to allow life to emerge? The laws of physics, the fundamental constants, and the delicate balance of forces all seem to align in a way that makes life not just possible, but inevitable. From the strength of gravity to the charge of an electron, every detail appears fine-tuned to create the conditions for complex chemistry and ultimately for beings like us to exist. This is the idea of a life-friendly universe, a cosmos where the ingredients for life are written into its very fabric. At the heart of this concept is the Anthropomorphic Principle, the idea that the universe's laws must allow for conscious observers to exist. In other words, if the universe weren't set up this way, we wouldn't be here to ask the question. But why is the universe so perfectly suited for life? Some scientists, like Martin Rees, have explored the idea that the physical constants we observe aren't random. They're the result of a delicate balance, a set of conditions that allow stars to burn, planets to form, and molecules to come together in ways that support life. To make this idea more tangible, think of the universe as a cosmic laboratory. Every experiment in this lab depends on precise measurements and finely tuned conditions. If the temperature is too high, the experiment fails. If the pressure is too low, the results are meaningless. In the same way, the universe's physical constants, like the speed of light or the mass of a proton, appear to be set just right for life to emerge. Tweak any of these values even slightly, and the delicate chemistry that makes life possible could unravel. This raises a profound question. Is life a rare accident, a one-in-a-trillion fluke, or is it a cosmic inevitability written into the laws of the universe? The multiverse theory offers one possible answer. If there are countless universes, each with its own set of physical constants, then it's no surprise that we find ourselves in one where the conditions are just right for life. In this view, our universe isn't special. It's just one of many, each with its own unique set of rules. But for us, it's the only one that matters. Physicists like Martin Rees have spent decades exploring these ideas, delving into the fine-tuning of the universe and what it means for the possibility of life. His work reminds us that the cosmos isn't just a collection of stars and galaxies, it's a dynamic, evolving system, shaped by forces we're only beginning to understand. The fact that we exist, that we can observe and ponder the universe, is a testament to its life-friendly nature. But here's another way to look at it. What if the universe isn't just fine-tuned for life, but for complexity itself? From the formation of galaxies to the intricate dance of molecules, the universe seems to have a knack for creating order out of chaos. In this sense, life might not be the end goal, but a natural byproduct of a cosmos that thrives on complexity. As we explore these ideas, we're reminded of the profound interconnectedness of all things. The laws of physics, the structure of the universe, and the emergence of life are all part of a grand cosmic story. Whether life is a rare accident or a cosmic inevitability, the fact that we're here to ponder these questions is a mystery worth celebrating. So, the next time you look up at the stars, consider this: you're not just a passive observer of the universe. You're part of its story, a living testament to the delicate balance of forces that make life possible. And in that realization, we find not just the beauty of existence, but the endless potential of discovery. If the universe is so unimaginably vast, filled with billions of galaxies, trillions of stars, and countless planets, why haven't we found any signs of intelligent life beyond Earth? This is the essence of the Fermi paradox, a question that has puzzled scientists and thinkers for decades. Named after the physicist Enrico Fermi, who famously posed it during a casual conversation in the 1950s, the paradox highlights a striking contradiction. Given the sheer size and age of the cosmos, it seems almost inevitable that intelligent civilizations should exist, yet we have no evidence of them. To put this into perspective, imagine the universe as a vast, silent forest. You know the forest is teeming with life, birds, insects, animals, yet as you walk through it, you hear nothing. No chirping, no rustling leaves, no signs of movement. It's eerily quiet, and you can't help but wonder, where is everyone? In the same way, the universe, for all its enormity, seems oddly silent when it comes to intelligent life. This silence has led to a range of theories attempting to explain the paradox, each offering a unique perspective on why we might be alone or why others might be hiding. One of the most compelling explanations is the idea of the Great Filter. This concept suggests that at some point in the development of intelligent life, there's a barrier so insurmountable that almost no civilization can overcome it. The Great Filter could lie in our past. Perhaps the emergence of life itself is extraordinarily rare, or it could await us in the future, a catastrophic event or self-destructive tendency that wipes out civilizations before they can make contact. If the filter is behind us, we might be among the lucky few to have made it this far. If it's ahead, the silence of the cosmos could be a grim warning of what's to come. Another possibility is that intelligent life is simply rare. Even in a universe as vast as ours, the conditions needed for life to arise, evolve, and develop technology might be so specific that intelligent civilizations are few and far between. Think of it like winning the cosmic lottery. The odds might be slim, but someone has to win. And in this scenario, we might be the winners, a rare spark of intelligence in a mostly lifeless cosmos. But what if the answer lies not in the rarity of life, but in the challenges of communication? Imagine trying to send a message across a continent without phones, radios, or the internet. Now scale that up to the size of the universe. The distances are so vast and the timescales so long that civilizations might simply miss each other. They could rise and fall without ever crossing paths, like ships passing in the night. Enrico Fermi's question, "Where is everyone?" has no easy answer, but it invites us to reflect on our place in the universe. Are we truly alone, or is there something preventing contact? Could other civilizations be out there, waiting for us to reach out, or deliberately avoiding us? These questions don't just belong to scientists, they belong to all of us. They challenge us to think about the nature of life, the future of humanity, and the mysteries that still lie hidden in the cosmos. As we ponder the Fermi paradox, we're reminded that the universe is full of questions waiting to be answered. Whether we're alone or not, the search for answers is a journey worth taking, one that connects us to the vast, silent forest of the cosmos and the endless possibilities it holds. The universe, vast and mysterious as it is, isn't just a static backdrop. It's a dynamic, evolving entity with a destiny written in the very laws that govern it. From the fiery birth of the Big Bang to the intricate dance of galaxies, the cosmos has been on a journey for billions of years, but where is it headed? What does the future hold for the universe? The answer lies in a delicate tug of war between two cosmic forces: gravity, which pulls everything together, and dark energy, which pushes everything apart. These forces will shape the universe's ultimate fate, leading to scenarios that range from the eerily serene to the catastrophically dramatic. One of the most widely accepted theories about the universe's future is the Big Freeze, also known as the heat death. Imagine a cosmic clock slowly winding down, its gears grinding to a halt as the universe expands and cools. Over trillions of years, stars will burn out, galaxies will drift apart, and the universe will grow colder and darker. Eventually, even black holes, those voracious devourers of matter, will evaporate, leaving behind only a faint, cold glow of radiation. It's a future of stillness and silence, where the universe's energy is spread so thin that nothing new can form or happen. But the Big Freeze isn't the only possibility. Another, more dramatic scenario is the Big Rip. In this model, dark energy doesn't just push galaxies apart. It accelerates the expansion of the universe so rapidly that it tears everything apart. Picture a cosmic fabric being stretched to its limit until even atoms can't hold together. Galaxies, stars, planets, and eventually the very building blocks of matter would be ripped apart in a catastrophic event that leaves the universe in a state of total dissolution. It's a stark contrast to the Big Freeze, offering a future not of cold stillness but of violent destruction. Cosmologists like Lawrence Krauss have spent decades exploring these possibilities, using the tools of physics to peer into the distant future. Krauss, a leading voice in the field, has described the universe's fate as a story written in the language of energy and entropy. He suggests that the interplay between dark energy and gravity will ultimately determine the universe's destiny, with the balance tipping in favor of one or the other over unimaginable timescales. To make these ideas more relatable, think of the universe as a cosmic hourglass. The sand represents energy slowly trickling from one chamber to the other. In the Big Freeze scenario, the sand runs out, leaving the hourglass empty and still. In the Big Rip, the hourglass shatters, scattering the sand into oblivion. Both outcomes are stark reminders of the universe's fleeting nature, even on timescales that dwarf human comprehension. So, what will the universe look like in 1 trillion years? Will it be a cold, dark expanse or a chaotic sea of shattered fragments? These questions don't just belong to cosmologists, they invite all of us to reflect on the nature of existence and our place within it. As we explore the universe's future, we're reminded that the cosmos is far more dynamic and mysterious than we often realize. The search for answers isn't just about predicting the universe's fate, it's about understanding the forces that shape it, from the smallest particles to the largest galaxies. And in that search, we find not just the secrets of the cosmos, but the endless potential of our own curiosity. Whether the universe ends in a whisper or a scream, the story it tells is one of beauty, complexity, and infinite possibility. What if the universe, in all its complexity, could be explained by a single, elegant equation? A theory so powerful that it unites all the forces of nature, from the tiniest particles to the vast expanse of space-time itself. This is the dream of a theory of everything, a unified framework that could explain the cosmos in its entirety. For centuries, physicists have been on a quest to uncover this grand equation, a quest that has shaped our understanding of the universe and driven some of the greatest minds in history to push the boundaries of human knowledge. At the heart of this pursuit lies a profound challenge: reconciling the two most successful but seemingly incompatible theories in physics: quantum mechanics and general relativity. Quantum mechanics governs the behavior of the very small, describing particles that can exist in multiple states at once, appearing and disappearing in the blink of an eye. General relativity, on the other hand, explains the very large, from the bending of light around massive objects to the expansion of the universe itself. While both theories have been incredibly successful in their own domains, they clash when applied together, creating paradoxes that defy explanation. Enter string theory, one of the most ambitious attempts to bridge this divide. Imagine the universe not as a collection of point-like particles, but as a symphony of tiny, vibrating strings. Each string vibrates at a unique frequency, creating the particles and forces we observe. String theory doesn't just unify quantum mechanics and general relativity. It suggests that all the forces of nature, from gravity to electromagnetism, are different notes played by the same cosmic orchestra. It's a breathtaking vision, one that could finally solve the puzzle of the universe. But string theory isn't the only contender in the search for a theory of everything. Other approaches, like loop quantum gravity, propose that space-time itself is made up of discrete, indivisible loops, creating a quantum fabric that underlies reality. Meanwhile, some physicists are exploring the idea of a multiverse, where our universe is just one of countless others, each with its own set of physical laws. These theories, though wildly different, share a common goal: to find a unified explanation for the cosmos. Albert Einstein spent the last decades of his life searching for such a theory, driven by the belief that the universe's secrets could be unlocked through mathematics. Though he never succeeded, his dream continues to inspire generations of physicists. Today, scientists like Edward Witten and Carlo Rovelli are carrying the torch, exploring new frontiers in the quest for unification. To grasp the magnitude of this challenge, think of the universe as a jigsaw puzzle. Each piece represents a different aspect of reality: gravity, light, particles, and more. For centuries, we've been assembling the edges, filling in the corners, but the center remains elusive. A theory of everything would be the missing piece, the one that completes the picture and reveals the universe in all its glory. So, will we ever find a theory of everything? The answer is far from certain. Some believe it's just beyond the horizon, waiting to be discovered. Others argue that the universe's complexity might forever elude a single, all-encompassing explanation. But whether or not we find the ultimate equation, the search itself has transformed our understanding of the cosmos, revealing its beauty, complexity, and infinite potential. As we continue this journey, we're reminded that the universe isn't just a collection of mysteries to be solved. It's a story to be explored, a puzzle to be pondered, and a source of endless wonder. And in that exploration, we find not just the secrets of the cosmos, but the boundless curiosity and creativity of the human spirit. What if the universe, in all its vastness and complexity, is not just a stage for existence but a story waiting to be told? And what if we, as humans, are the storytellers, the universe's way of understanding itself? This is the profound idea at the heart of cosmic self-awareness, the notion that through conscious beings like us, the cosmos becomes aware of its own beauty, mystery, and meaning. From the tiniest subatomic particles to the largest galaxies, the universe unfolds its secrets, and we are here to observe, interpret, and wonder. Think of humanity as the universe's eyes and ears, its way of seeing and hearing itself. Just as a mirror reflects an image back to us, we reflect the cosmos, observing its grandeur and pondering its mysteries. This idea ties closely to the Anthropomorphic Principle, which suggests that the universe's laws are finely tuned to allow conscious observers to exist. But it goes deeper than that. It's not just that we can observe the universe, it's that our ability to observe and question gives the cosmos a kind of self-awareness, a way to know itself through us. Carl Sagan, one of the most passionate voices in science communication, often spoke of this connection. He famously said, "We are a way for the cosmos to know itself." Sagan saw humanity not as mere spectators but as active participants in the universe's story. Through science, art, and exploration, we uncover the universe's secrets, weaving them into the fabric of human understanding. In this sense, our curiosity isn't just a human trait. It's a cosmic one, a reflection of the universe's own drive to explore and comprehend. To bring this idea to life, let's imagine the universe as a vast library filled with countless books. Each book contains a piece of the cosmic story, from the birth of stars to the formation of galaxies. But without someone to read them, the stories remain untold. Humanity, in this analogy, is the reader, the one who opens the books, deciphers their meaning, and shares their tales with others. Our role isn't just to exist within the universe, but to give it a voice, to make its stories known. But this raises a deeper question. What is our purpose in the grand cosmic story? Are we here simply to observe, or is there something more? Some thinkers argue that our role is to create meaning, to find connections between the stars and our own lives. Others suggest that our purpose is to preserve and protect the fragile beauty of the cosmos, ensuring that its story continues for generations to come. Whatever the answer, one thing is clear: our existence is intertwined with the universe in ways that are both profound and humbling. As we explore these ideas, we're reminded of the incredible responsibility and privilege of being conscious observers. Every discovery we make, every question we ask, adds a new chapter to the universe's story. From the first humans who gazed at the stars to the scientists probing the depths of space today, we are part of a legacy of curiosity and wonder that stretches back billions of years. So, the next time you look up at the night sky, consider this: you're not just a passive observer of the cosmos, you're a participant in its story, a thread in the tapestry of existence. Whether through science, art, or simply the act of wondering, you are helping the universe understand itself. And in that realization, we find not just a sense of purpose, but a connection to something far greater than ourselves, a cosmos that, through us, is learning to see, to hear, and to dream. From the explosive birth of the universe in the Big Bang to the mind-bending possibilities of the multiverse, we've journeyed through some of the most riveting theories about how everything came to be. Along the way, we've explored the cosmic web, the first stars, and the mysterious forces of dark matter and dark energy. We've even dared to ask if the universe itself could be alive, a thinking entity aware of its own existence. Each theory offers a unique lens through which to view the cosmos, revealing a universe that is not only vast and complex but also deeply interconnected. What stands out most is the sheer scale of these ideas. The universe isn't just a collection of stars and galaxies, it's a dynamic, evolving story, one that began billions of years ago and continues to unfold with every passing moment. From the tiniest quantum fluctuations to the largest cosmic structures, every piece of this puzzle reminds us of the awe-inspiring mystery at the heart of existence. And while we've made incredible strides in understanding the cosmos, there's still so much we don't know. That's the beauty of science. It's a never-ending journey of discovery. Each question we answer leads to new ones, keeping us humble and curious. Theories like the Big Bang, cosmic inflation, and the multiverse don't just help us understand the universe, they help us understand ourselves. They remind us that we are part of something far greater, a cosmic tapestry woven from the threads of time, space, and energy. As Carl Sagan once said, we are a way for the cosmos to know itself. Through our curiosity, our science, and our imagination, we give the universe a voice, helping it to reflect on its own beauty and complexity. And in doing so, we find a deeper connection to the cosmos and to each other. So, what do you think? Do you believe the universe had a single beginning, or is it part of an endless cycle of creation and destruction? Could there be other universes out there, each with its own set of laws and possibilities? I'd love to hear your thoughts in the comments below. Don't forget to subscribe and hit the notification bell so you never miss a deep dive into the mysteries of space. Together, let's keep exploring, wondering, and uncovering the secrets of the cosmos. After all, the universe's story is still being written, and we're all part of it.